All right, we're going to go ahead and get started. Welcome everyone to another CPTC meeting. Again, we have our meetings every Tuesday at 6:30 p.m. So just a couple things to know. Make sure you join the Discord. We're going to do it. It's where we do a lot of hack the box and try hack me collaboration stuff. And then any specific topics you'd like to learn related to pen testing or red teaming or anything you'd like to teach about, you can enter in that Google Sheet. I'm going to post a link again in the Slack and Discord after the meeting, so you guys can fill that out if you guys have any other ideas. We have a few people left on the list who want to present, so I'm going to try to get those people started to present in the coming weeks. But we've really used some more ideas. So if you guys have any, just put them in the Google Sheet. And so what we're going to do today is Connor Callan's going to be presenting on binary exploitation part 2. If you didn't see his part 1, that's okay. I'm going to be uploading a video of it on the UFC YouTube channel within the next week or so. It should be up on there. But yep, this is going to be part 2. So I'll stop sharing my screen so you can start sharing, Connor. Okay, and then make you a co-host. Right. Are you able to share your screen now? Okay, awesome. If you're talking, Connor, we can't hear you, or at least I can't.
Oh, can everyone hear me
Yep,
now?
you're good.
Oh, my mic was muted. Perfect. All right. Everyone can see my screen, right?
Yep.
How do I? All right. All right. So this is binary exploitation part 2. If you didn't see part 1 of my workshop, as John mentioned, he's planning on uploading it. You still could probably get a little out of this, although I'm going to be assuming that you understood most of the things in the part 1 workshop, because this is, of course, a part 2 workshop. And we're going to be doing a few things differently from last time. So first of all, this time there will only be demos that we do together rather than a try it yourself section. I did think that was pretty successful, but the problems are just going to be getting harder. So I just don't think we have the time for people to spend an hour working on a problem. So we're going to have demos that we do together this time. Additionally, this time it's going to be a lot more time spent on the demos and a lot less time spent on the slides, because really I don't have much more to say in the slides other than just go over the topics that we didn't learn last time and then demo some problems. And this time we're going to actually be demoing, rather than my contrived problems, actual real problems, 2 from a previous CTF, as well as 1 retired hack the box challenge if we get to it. So without further ado, I am going to jump right into it. And we're just going to be talking about a few topics that we missed last time. I'm going to go over them briefly. And then when I actually do the demos, I'll give like a more in-depth explanation with examples, because then you can see it actually working in the demo. So we learned a bunch of stuff last time about buffer overflows and being able to overwrite the return pointer on the stack. But sometimes just being able to jump to one location isn't good enough. So this time, we now are going to introduce a tool called return-oriented programming, which is a technique that was developed to get rid of this limitation. So imagine if, instead of just being able to jump to one location, I could actually pull off a series of operations when I got my buffer overflow. Well, that's what return-oriented programming lets you do. So return-oriented programming is based on using what we call gadgets. So gadgets are, you can see on the left-hand side of my image here, there's some examples. Gadgets are short snippets of code followed by a return instruction. And the reason this is so useful is because if you just write a bunch of return addresses on the stack, then you can jump to one of your gadgets, it'll do some code or whatever, and then it'll return, and then your, sorry, I'm a little sick, and then it'll return to the next gadget, and you basically can just chain a bunch of gadgets, and they'll allow you to do something in the code that you wouldn't be able to by just jumping to one location. This will be really useful when you need to set up registers in some way, or perform a syscall or something like that, in more difficult binaries where you can't just jump to one location and automatically win. There are also tools, of course, to find gadgets in binaries, which I will be demonstrating one of them later today. And that's mostly that for that. And now I'm going to talk also a little about the protections. So if you remember last time, I did go over the NX protection, which is basically saying that you can't put code on the stack. It has to actually be in a real text or code segment. But now I'm going to quickly skim over the other protections that we just ignored last time because they were all disabled, because today they won't all be disabled. So the first one is a stack canary. So the stack canary is a particularly bad protection to see on a binary that makes it significantly harder for us pwners. Now, what a stack canary does is it puts a canary right at the end of the stack, right between all of the stuff on the stack of the buffers and local variables and the return address and base pointer. And the reason that it does this is because right before it returns from the function, it checks the value of the stack canary. And if the value's been changed, then it knows that a buffer overflow occurred and your program will just crash. It just terminates. So a stack canary is very bad for us because we don't know the stack canary and you only get one shot typically to overwrite the stack canary, and it's 7 bytes. So you're very unlikely to guess it. Like, it's not really like brute forceable or anything in most cases. So that would be very bad for us. Now, there are some things about the stack canary that help us as pwners in the long run. So one thing is that the stack canary is the same for the entire binary. So if you can somehow leak the stack canary, it'll be for every single function uses the same stack canary. It's initialized when the binary starts, it's randomized, but then for every single function, it's the same. And another technique that's often used to defeat stack canaries is that when the program forks, the stack canary still remains the same. So say you have a program that accepts network connections and it forks off a new process to handle each connection. You can test the stack canary on one of those forks, and then you'll know whether or not you got the stack canary right, and you can brute force the stack canary this way because every fork will have the same stack canary. The next protection that I'd like to talk about, oh, whoops, wrong way, is rel-row, or first I'm going to talk about the PLT and GOT, and then I'll explain what rel-row is. So now you may know that when you're programming, there won't only be functions in the binary that you wrote. There are other functions from other libraries. Particularly, there will probably be functions from the C standard library known as libc. And if you remember last time, I actually went over an attack called return to libc, where we return into a function from the libc binary, which or returning the code in the libc binary rather than the code in our executable. Well, when you run a program on Linux, at least, how does it know where the functions are for the libc? Well, the way it works is that there's a section in memory in the binary called the procedural linkage table or something. It's called the PLT. And I think that's what it stands for. And what the PLT does is the code in the binary calls the PLT, and the PLT actually deals with the pain of loading in the library and the linking up the functions. This is somewhat of a simplification, but it doesn't really matter that much. But what you need to understand is the PLT is the code in the binary that that the program jumps to call functions from external libraries. And the GOT, or the global offset table, is actually the part of the PLT that stores the addresses for the functions. So if you take a look at this example image here, you can see a code in a binary will call a function in the PLT, and the function in the PLT will sometimes, if it's the first time, it'll actually call this resolver function, which just links up with like the library loading stuff and figures out where it is in memory. And after that, what it does is it will jump into the GOT. It'll take the address from the GOT and it'll jump there, and that'll be where the function is. So, of course, if you're a pwner, you might realize, oh, well, if we could overwrite the PLT, instruct the code in the PLT, that would be pretty good for us. And another attack that's potential, and this is a pretty common one, is what if we were able to overwrite this GOT address right here? Well, this address is where the code will jump to when a function gets called. So if we were to overwrite that, we'd be able to essentially take over any call to that function, which would be very good for us usually. And additionally, one third thing that's useful about the PLT and GOT is they can be used in attacks to defeat pi, and we'll talk about pi in a later slide, so I'll leave discussing exactly how that works to then. And by a later slide, I mean right now. And I don't really have an image for this, so it's just a picture of a pi. But you may remember ASLR previously. And what ASLR does is it randomizes where things are in memory. So the stack is at a random location of memory, the heap is, and this is really annoying for us pwners because we want to know where things are in memory because obviously we're going to need pointers to other stuff for that for our pwning. Now pi is actually an extra bad version of this, which some binaries, most binaries nowadays will have, where the code in the binary is actually at a random location too. So previously, you may remember when we were pwning, we could just easily determine the address to the function and pass it into our exploit. But if the binary has pi, then we can't just easily determine the address of a function because all the functions in the binary are random. So we actually have to leak the base and then figure out where the functions are based on that, which I think I will demonstrate in one of the examples today. Now, why I said that the GOT and PLT are very good for pwning is that the GOT and PLT are actually not affected by pi. They're in the same location always. So therefore, if you're able to control the return pointer somehow, or the function pointer just where the code is in any way, you can go into the GOT and PLT and you can call functions through that, and you don't need to know any of the offsets or bases or anything because there's no pi protection. And I don't have slides for these, but I will demonstrate real quick two other things. So I'm going to talk about calling conventions real quick. And I just have this Wikipedia page open. If you ever need to remember the calling convention for Linux, it's really useful to just go to this x86 calling conventions Wikipedia page, and they have a table right down at the bottom. So now previously what I told you was that arguments were passed on the stack, but in 64-bit, this is actually not true. Arguments are actually passed in registers, CPU registers, and not on the stack, or at least the first few arguments are passed in CPU registers. And we can see for Linux on x86 64, the arguments are actually, the first argument is passed in RDI, then RSI, then RDX, then RCX, then R8, then R9. And these registers are used for floating point, and then everything after that is passed on the stack. And therefore, this will be very useful for you to know, because if you're trying to call a function on 64-bit, you can't just put your arguments on the stack. You have to actually put them in registers. And how will you do this? Well, if you remember when I mentioned return-oriented programming before, where we could call small snippets of code, well, you can use return-oriented programming to set up your registers for the calls. You also can see the Microsoft calling conventions on here too. We're obviously doing only Linux binaries today, but if you ever get into that, the Microsoft calling conventions are on this page as well. And one other thing I'm going to talk about is this Libsy Database website. So sometimes when you do a challenge, you won't be given the libc binary, but you want to know where the functions are in the libc. Now, one way you can actually combat this is if you can leak the address of certain functions in the libc, you can put it into this Libsy Database website, and it will search through all the libcs that it has in its database, and it'll find the libc versions that have those offsets. And this is very useful, and I believe we will be using this in one of our pwns today. Now, I'm actually going to jump right into the pwning now, right after that. I'm going to quickly upload a zip file of today's demos should people want to follow along, and I recommend you follow along, of course, if you already have an environment set up, because it will definitely be beneficial for your understanding. And I'm going to jump directly into the first demo. Today, we just have the binaries. These are actually two, like I said before, two challenges from previous CTF, as well as a retired Hack the Box challenge. Hopefully, we'll get through all of them. The first one is just a simple warm up. It's a buffer overflow, basically what we did last time, just to, for everybody to remember how to pwn. And then the second two will actually go into the more advanced techniques that we talked about today. And you don't have the C source file today because there actually are no C source files, because these are literally just random challenges I downloaded. And I actually haven't done this challenge either, myself. I did skim over the write up to make sure there wasn't any crazy things going on, so like it would be appropriate for today's workshop. But we'll be seeing a live solve today by me as well. So hopefully that will help you get some insight into how you can think when you're poning as well. So first thing I'm gonna do is I'm gonna open it up in Ghidra. And while I'm waiting on that, I'm actually just gonna run the binary real quick to see what it does. We can see that it asks me to put my name in, and it prints out my name. I guess the first thing I would try in this case is I would just try inputting a really large name to see if it crashes. That appears to have worked, although I wonder if I run, whoops, not my game.
Hey, Connor, people are asking, are you able to zoom in? It's a little hard to see with the small
Yep,
text.
sorry.
No worries.
This better?
Yeah, thanks.
Sorry, I forgot about that. So I'll just, if I do this, yeah, I can print a large number of A's with Python, and I'll pass that into the binary. Oh, and we can see it's seg faulted. So that means that there's probably some sort of buffer overflow going on where I'm able to overflow the buffer with this number of A's. So now I will go look at it in Ghidra real quick, and I'll just run the default analyze. And we'll see, okay, fortunately, it's not even stripped, which is good for us. Okay, so we see we have a buffer, 140 characters, but we use getS, which doesn't have a limit of how many characters we can read in. That's very good for us pwners because that means we can be reading in as much as we want. So, all right, so yep, this seems pretty simple. And then I'm also going to run checksec real quick. If you have pwn tools installed, you can just use pwn checksec, which will let you check the protections on it. And we can see this is extra good for us because there's no rel row, which means that the GOT and PLT are completely overwritable. There's no Canary, like I mentioned, NX is enabled, and there's no pi. These are all very good for us because that means this binary will probably be relatively easy. And also one other thing I noticed, but I didn't mention earlier while I was looking in Ghidra, was there's actually a shell function which spawns a bash shell. Or well, I guessed it would spawn a shell because it was called shell, but now I clicked it and I can see it spawns a bash shell. So that makes this binary even easier actually, because it means we don't even have to like do our own pwn. We just have to get to this win function. So this is really just a simple ret to win, like I demonstrated last week. And I'm really, like I said, I'm just doing this as like a warm up. So I'm gonna create my solve script real quick. I actually use a tool called Pwnit. I highly recommend if you get into pwning, which will automatically create a stub solver script for you. And I believe what I remember right, so if I look in Ghidra, back at the main function, this buffer is hex 90 from RIP. So if I, let's see, I need to write hex 90 characters, and then I also need to write the address of the shell function, and hopefully we can see if I'm good enough to get this in one try. Oh, and I have done something stupid. Oh, I forgot to pack my address, of course. Don't forget to, oh, is this 32-bit or 64-bit? It's 32-bit, always good to check. I almost used the wrong packer. That would have been bad. So I believe this probably, oh, whoops, and I just forgot to run it locally. I got EOFL reading and interactive, which means I actually did something wrong. So I guess that means that I will be actually debugging my script instead of just attempting it on the first try. And let me just set up my terminal so I can actually use this. And oh, whoops, I need to add a gdb.attach. And gdb.attach, if anybody doesn't remember, in pwn tools just lets you attach a gdb session to your running binary. And I keep forgetting to run in local. Okay, so we can see we're in GDB. I'm just gonna continue. And let's see, cannot disassemble from PC. Okay, so it looks like I wrote too many A's because you can see 4-1 is actually the like that's actually an A, so it looks like I actually wrote too many A's. Which is weird because Deidre says that the buffer is 90 hex away from RIP. So let's see how many, let's see. But sometimes it may have made a mistake. Oh, whoops. So we can see that, whoops, what do I want? No sign, RSP minus 32. Oh boy, did it already fuck up all my shit? Okay, I'm just gonna rerun my soul script. And I'm gonna break point in, let's see, I'm gonna break point right after main, right after the return from gets, which will allow me to see what the stack looks like. And telescope is a useful command if you have Jeff installed, which just lets you look at the stack. Let's see, so we can see that I appear to have gone too far because we would expect, I believe I've gone 4 bytes too far, if I'm looking at this correctly, because if this is the save, EBP will typically be at the saved EBP, which should be right here. So that means we would expect the saved return address to be right here. And if we continue, we should see that the stack should end up at this address, which it does appear to. Oh, whoops, there we go. Just that finger might close. So I'm just gonna try writing 4 less bytes. And we'll see how that goes. Oh, and I did something stupid. Oh, oops. Actually remember how order of operations works. Okay, and this is good. Detaching after vfork indicates that it did execute something. So we're probably in a shell now. Whoops, if I could type in the right terminal. And we are, so we can see that we have successfully pwned this binary. And if I just change my shell script and remove the gdb.attach, I will be able to, oops, if I run it locally, we can see that I do successfully spawn a shell. And if anybody wants to test their exploit locally, or remotely, I actually do have a remote server running this time, which I will actually run my test against real quick to see if my pwn is working. And we can see it does. Oh, there's even a flag in here from the challenge. You can see this is actually a challenge from Encrypt CTF. This is where I stole it from. And we can see that my exploit does work on remote, which is good for us too. And yes, so that is the first challenge, basically just a warm up, reminding everybody how to pwn. And we're now going to get into the second challenge where I will hopefully actually demonstrate some of the new pwning techniques that I was just talking about, rather than the first challenge. So first thing I'm going to do is just initialize my Sol script real quick. Or whoops. And I will open up the binary in Ghidra so I can close out of this. And I will analyze it real quick. We'll see the functions, and fortunately not stripped again. Oh, maybe partially stripped. Okay, so we have main. I guess I can also run the binary. That's another good thing to do, is to run the binary like when you first get it to see what it does. So we just provide, it reads into a buffer. Let's see, it reads into a buffer, hex 90, file .3, same thing. It's a 32-bit. I'm gonna check sec this real quick. And we can see that it does not have any protections as well, so that's good for us. But unlike last time, there is no easy shell function. So that's going to be a little bit bad news for us, and it's going to make it a little bit harder. Additionally, you'll notice that unlike previous challenges where I did last workshop, we don't have an easy leak of libc. But we actually do have an easy leak of libc by using the PLT and GOT that I mentioned before. So what I'm going to do real quick is start. I already got my solve script. And also one thing I'm going to do is immediately put in the remote address, because this is one where the libc version on the remote actually does matter. So what I'm going to do is we can see, so we can overwrite if it's the same as last time, which it looks like it is. We'll be sending hex 90 minus 4 like last time to get to RIP. But this time, obviously, we don't have a shell function to go to where we, and it's even though it's no pi, there's not really anywhere in the binary that's useful for us to go to. But what we can do is we can go to the GOT and PLT. So what I'm going to do is I'm actually going to go to exe.plt for puts. And then I'm going to go to, and I got a P32 that, of course, to change it into a pointer. And then I'm going to go to P32 of exe.plt.got for, let's just say getS. It doesn't really matter which function I choose as long as I remember. And what this is going to do is it's going to write what it's going to do is it's going to call puts because it's going to jump to the PLT for puts. And then after that, it's going to the argument, which will be passed on the stack. And by the way, I mentioned this earlier about how in x64 arguments are passed via registers. For the PLT, it's always passed on the stack. Or wait, no, what am I saying? I'm sorry, I'm just lying. But what we're gonna do is we're gonna have puts, and then we're gonna have the getS address. So what it's going to do is it's going to call puts with the address of getS from the GOT. So the PLT, remember, is where the code that actually calls the function is, and the GOT is where the address of the function is. Now what this is going to do is it'll tell us the location of getS in libc, which will allow us to calculate the libc base and therefore call functions in libc. And additionally determine which version of libc is running on the remote. Because you can see in this challenge, I actually, whoops, what am I doing? I didn't actually get a libc version. So one thing I'm also going to do real quick is I'm going to not use send line. Actually, I think it might be necessary here for running on remote. And one additional thing I'm going to do though is I'm going to go to the main function afterwards. So what this essentially does is it basically lets us just get a loop. So what it'll do is it'll call puts with printing out the address of getS, because that's the parameter. And then after that, after puts, the next return address on the stack will be main, which will go back to main, which will basically let us re-exploit the binary. But now at that point in time, we'll know what the address of getS is. And what I'm going to do also real quick is I'm going to change context.log level to debug. And this is a useful pwnTools trick that will allow you to view all of the information that's sent to and from the binary. So we can see that we got what looks like a pointer printed out, which means that we are definitely doing good. So what I'm going to do now is I'm actually going to set up, I'm going to actually set up the, I'm actually going to write my script so that I can extract this pointer real quick. So what I'm going to do is I'm going to use recv until, and it'll look for dessert. And make sure that works real quick. And then this will just read up until where it says some sweet dessert right here. And then what I'll do after that is I'm going to try to extract the pointer. So r equals recv, or what's I call it, like leak equals r dot recv until, and it should be until a new line is good. And then we'll cut off the new line. And then we're going to print the leak out. And I'm just going to turn off the context log level to stop spamming my terminal real quick. And we can see it is printing out what looks like a leak. Although it does appear like there may be some extra characters here. I'm going to print out, let's see. I'm going to print out the length of the leak right now real quick. I think what's going on actually is that our leak is too long. Yes, of course, it's 9 characters long, which would be too long for both 64 and 32-bit, and we're 32-bit. So what we also need to do is we actually need to, instead of just cutting off the last character, we're just going to cut it to 4 characters exactly. Okay, so that's much better. And then we're going to use U32 to unpack our leak, and we'll print it out, and then we'll print out the unpacked version. And we can see that we have extracted what is hopefully the pointer to, what was I printing out? Get S. So what I'm going to do real quick is I'm going to go to the Libsy Database, and I'm going to put that in for get S and see if we can find anything. And oh, whoops, it appears that I may have made a mistake because it actually does not find it. So that is a good, so that means some nice live ponying real quick. So if that's the case, then what I'm going to do is I'm going to actually run the binary locally and see what is going on and see what my mistake is. And let me just set up my terminal. So oops. And I'm going to breakpoint on put s, and I'm going to continue. And we can see that we are calling put s. Let's see. We're calling put s. And what's on the stack is this. Where is this? Info outer, or whoops, info symbol. Global offset table in section. So it appears that I maybe have. Oh, I've already gotten past the point where it gets pushed correctly, haven't I? So I actually need to break point earlier than that to see what's going on. So I'm actually just going to break point right after the get s returns. And then I'm going to look at what the stack looks like. And of course, I need a lot. So we can see it's going to return into put s. And it does appear like it should be returning into get s. It does appear like it should be printing out this get s. Except that it does not print out get s. Is there like a dot command? Okay, yeah. Interesting. Oh, I think I know what I did, stupid. I believe that this should actually be. So yes, you can see that pwning is not always easy, and sometimes you make mistakes. And as I'm doing this challenge live to try to give everyone insight into it, I appear to have made a mistake. Oh, I made some typo. Oh, I forgot to. Okay, so this probably is the actual. Yes, okay. So we can see that this time the leak actually does work because when I run info symbol, it tells me it's getS. And for anybody who didn't understand my stupid mistake, of course, the parameter is actually passed after the return address. So when I'm calling putS, I put the return address first and then the parameter I want to pass to putS. So what I was actually doing before was I was calling main. I was printing out the address of main, and then I was attempting to jump to the GOT of getS and crashing afterwards. So that's why my code wasn't working at all. So now if I run, whoops, I need to get rid of my GB attach to run it on remote. So now if I run it on the remote, I should get an actual leak for the getS function. And hopefully when I put this in the Libsy database, okay, I get an actual Libsy. Now, sometimes you'll actually need to put in multiple functions. I actually got really lucky this time where I only put in one function and I got an instant match, which is definitely very good for me. And the Libsy database website is actually really cool because we can see that like, so if we have the address of getS, it'll show us the offsets to the system function and also to a bin.sh string in glibc. So these offsets are really useful because that'll allow us to just quickly program up our exploit real quick. So if I go into our exploit real quick, now we'll have our leak. Actually, I'll just keep that print function in there. And this time, of course, we need to send the A's again to overflow because we're back in main, if you remember right, because we returned back into main from our first stage of our exploit. But this time we have the leak, and we also know which version of libc it is because of this Libsy database search. Now, if it was a harder problem, I would actually download this libc and then I would set up my local environment to use it. But this is actually a pretty easy challenge, so I probably don't need to do that. So what I'm going to do is I'm going to call into the system function. So I'm just going to copy the difference. So that's the difference from the getS function if I have it. So easy. And then I need a return address, which I'm just going to make 0. Like it just needs to be there, obviously, but it's not like actually anything relevant. And then I'm going to pass to system as the only argument is the bin.sh string. And again, that's this difference just lets me see the difference from the address that I've already leaked from libc. And then hopefully, if I know what I'm doing, this right here should pop a shell on the remote. And I got EOF reading interactive, which means that I probably did something stupid. So we can see we're heading to the system function, and we have a return address. I don't actually know why this doesn't work, so I guess we're going to get the expert demonstration of finding out how you set up your libc locally. So to set up your libc locally, we're going to need to download the libc. Oh my god. Why is this so slow? But so I'm going to download the libc from the Libsy Database website. And while that's working, I'm going to see if I did something stupid. No, I don't think I did anything stupid. I guess one thing we can use to check if the libc database what? Am I dumb? I don't know what just happened there. Well, I guess I'm restarting that download. I tried to put it in the background, but I obviously screwed something up. Oh, it looks like it finished almost instantly this time. Perfect. So one thing that we can do to check if where stuff is wrong is I'm actually gonna take this offset and subtract it from our leak. And we can see that that offset is 4K aligned. So that means that this probably is the correct libc, or at least close to it. But for some reason, these offsets don't seem to be working, or I did something stupid in my exploit, which is entirely possible. So I'm also going to turn on the debug log level to see if I get anything useful from that. So we can see what it is doing is that it's actually just crashing on the second payload that I'm sending. Which is definitely not good. I'm gonna, so let's see. So yeah, I'm just gonna debug it locally, I guess. So another useful thing about Pwnit is it'll automatically get the right linker for your libc, because if you have the wrong linker, it'll just crash, which is a pretty epic experience. And then one thing I'm also gonna do is I'm just gonna trick it into thinking I don't have a solve.py, so I can just copy paste this stuff. Which will have the automatic setup for me. Paste that into my binary. And then also I want this for my local process, which will automatically set it up to use the correct libc. You can also, of course, sorry. You can also, of course, do this manually. Oh, did I do something stupid? Yeah, I did. Okay. You can also, of course, do this manually. So you can just run with the linker and then LD preload the libc, which will automatically set it up to use the right libc. LD preload is basically just a way of saying like you use this library instead of the one on your like the default system one. And now if I go to solve, I am going to attach a GDB right here, and I'll see why my exploit isn't working. Oh, I forgot to run locally.
Yeah.
And also this isn't gonna, I don't have tmux running, so obviously. All right, so where am I? I'm inside getS. I believe this should be back in main, so I'll continue until after the getS calls, and then I'll check out the stack. And, oh, interesting. Maybe I wrote too many this time. So if so yeah, we can see that I actually wrote where it's trying to return from. The system function is actually 8 bytes down on the stack, which means that I wrote 8 bytes too many. Now, what's interesting is I actually wrote the same amount. So I am unaware of why I would actually need to write a different amount. Maybe I'll investigate that later, but for now, we'll just see if this works. And see, all right, so that's right after the getS. Okay, so we can see this time it's going into the system function when it returns. You can see Jeff has this useful view where when it returns, it'll show you where it's going. And it does appear like binsh will also be the parameter. And we can see Jeff also has this useful thing where it'll show you the binsh, like the parameter to the function. So hopefully this means that now when I run it on remote, it should this time actually work. Oh, and I forgot to get rid of my gv.attach. Of course, I can't forget to do that. And it does appear this time that my exploit has gone off successfully as well. And there we go. So this is actually a pretty like standard template problem on CTFs. You'll see where what you need to do is you need to leak a libc and then use that leaked libc to call system, or I could have attempted a one gadget. I actually wanted to show this alternative technique of calling system with the binsh pointer rather than using a one gadget. I'm not actually sure why I need to use different values to overflow between these two. Maybe if I have time later, I'll look into it. But that's the great thing about being a pwner. Once we get to a point where it works, we don't actually have to care about why it works or why it doesn't work. So now we're going to get into the third demo and final demo of the day. And I'll try to go a little bit quicker with this one because I see that we're 50 minutes in, so we don't have that much time left. So I'm going to close out of Ghidra. And I will be analyzing this binary real quick. And this binary is one that I actually have previously solved, but it was so long ago that I've forgotten the solution by now. So again, one thing that's useful to do when you first solve a problem is, let's see, so we're going to run it. We can see that it runs that, but what I'm going to do is I'm going to generate a large number of characters with Python and pass it into the binary, and we get a seg fault. So that probably indicates that it's a standard buffer overflow attack. So, but this is a stripped binary, so we can see it's a little bit more difficult to reverse because all our functions are garbage. Now, one easy trick on Linux to find where the main function is if you go to the entry point of the binary, you'll probably see it calling libc start main. And the first parameter of libc start main is actually the main function. So now that I know that this is the main function, I can rename it as main. And we can see what happens. So we can see main calls this function. So this just sets some set vbuff. So I'll call this like setup vbuff or something like that. Like it doesn't actually do anything very relevant. The reason people do this set vbuff stuff on pwn challenges is just to make like it easier and more consistent, so that you don't randomly like not get anything printed out. So we can see it prints out, please don't hack me. And it does appear, interesting. I think this is just a garbage from, yeah, okay, see. And then it does a reads, and then it does a read syscall, and it uses 0, and that's standard in. I happen to know that by default. If you see, you'll probably recognize this. It reads into this buffer of 208, and it reads 500 characters in, and of course 208 is less than 500. And then it attempts to read a variable, and it checks if it's debug. And if it is debug, it will print out, it'll actually print out the pointer to your buffer and then recall main. Now, this could actually be potentially useful for us to be able to. So I think what I can do to test that is if I just send in debug, yes, it'll allow me to leak the address of my buffer on the stack. Now, this may or may not be useful, but we'll find out when we pwn the rest of the binary. So now it'll call this function, which looks like some obfuscation grab. So I'll call it like do obfuscate. And what it's passing into this function is, if I remember right, it was the address of our buffer. I might as well just rename this to buffer, to be honest. And yes, it passes in the address of our buffer. And so what it does is, so this parameter is actually going to be the buffer. And we can see what it does is I see. So what it does is it takes the pointer to it, and it looks like it keeps looping until the address, until it's a null byte, which would probably indicate the end of our input. And then this seems to be some sort of counter, it looks like. Yes. So this seems to be some sort of counter or index. I guess I could call it index. Might be better. And let's see. So what it'll check is it'll set the, so it'll do strlen on our buffer. It'll keep looping until the buffer, until the index reaches the length of the buffer.
Hey, can anyone hear anything?
Yeah, I was about to ask that. He cut out. I think he lost the internet or something because he's not in the meeting anymore. I'm guessing he'll probably join back in a second. Hopefully, if his internet's back up, I'll send him a message right now.
Yeah, what if he doesn't realize?
He just keeps talking. Let's see. Oh yeah, he knows it crashed. He's gonna join back now in a second. Oh, here he is. Cool.
Hello?
Yep, we can hear you.
Can anyone? Okay, my internet just randomly cut out, so that was epic.
No worries.
I guess I'll go back to my ponying talk now. So I think what I was talking about is, okay, so we have this obfuscator function. It loops through everything in the buffer, and then it adds or subtracts a value based on what the value is. So obviously we're going to need to reverse this obfuscation if we want to be able to send our payload. So that will definitely, and let me see how they read in. Let me see, because we can see it uses strlen. So I need to check real quick, but so this is actually, so we can actually bypass this pretty easily, because we can see what it does is it uses strlen of the buffer. And strlen actually just reads up to a null byte. The way strlen works is it just goes until it gets to a null byte. However, if we look in the main function, we can see that it actually is using a read call. And read is a syscall that just reads in. It'll just read in 500 bytes. It doesn't stop in a null byte or in the white space or any nonsense like this. When you're a pwner, this is like the most optimal line for you to see, because it means that you don't have to worry about null bytes in your input or something. So if we just put a null byte in our input, then what it'll do is it'll just bypass the obfuscation completely, because it'll just stop at that null byte, and then none of our stuff after that will actually get obfuscated, which is definitely good for us. So what I'm going to do real quick is actually get back into my stuff. And then I'll just use pwninit like I've used before to quickly set up a solve script and get into tmux. And I don't actually have a remote for this one because this is an old pack the box challenge, and they didn't provide a Docker file for me. So we'll be doing this all on local. So I'm just going to change this function to always return the local version. And now, so it does, if, so typically this value in Ghidra will be how much you need to overwrite to get to RIP. We can see on the last binary we did, that's not always true, but it typically will be. I can just use send instead of send line because read doesn't need a new line or anything. And I'm going to send in just a bunch of A's. Actually, I'm going to use null bytes because I don't actually want the string to get obfuscated. Times D8. Well, I'll just use like a null byte at the beginning. Then I'll use A, so that way I can easily recognize my buffer. But I need to do one less character, of course, because I'm starting with the null byte. So this null byte will just gimp their obfuscation mean, which is good for us. And then let's see. I don't think this debug actually helps us because it gives us the pointer to our buffer, but if we run, I guess we can check checksec, pwn check sec rot v2. Wait, what? Oh, I misspelled checksec. We can see it does have NX enabled, so we can't like jump to our buffer or anything useful like that. We can see that it doesn't have pi though, so that's definitely helpful for us. So this actually will probably, because we don't need to bypass this obfuscation, this will probably be pretty similar to the previous attack. We could solve it in a similar way. However, I believe that this is actually a 64-bit binary. So when we want to pass parameters to functions, it will be a slightly more difficult experience than just being able to like just being able to pass them on the stack. So I'll show you what I mean. I'll show you what I mean after that. So we're going to use the same trick as before, where we go to the PLT for, does it have putS or something useful like that? Printf. Printf is equally like as good as putS. It's basically just a more powerful version, but we don't actually care about any of like its more powerful features. And I'll actually just I'll print out the address of printf with printf. And I'll go back. Oh, actually, I actually need to put in the main address manually because it doesn't have symbols as we discovered earlier. So we'll see if this works. And it looks like, yeah, I did something stupid as usual. I forgot to pack these addresses, of course. And I also did something stupid again. Oh, I forgot to use a byte string. Really screwing this one up. And I'm actually going to switch this to being, while I'm here, I'm actually going to switch this to being debug log level. Do that. I got UFO reading interactive. Oh, of course, because being stupid. I made the same dumb mistake as last time where I actually, what's it called? I forgot that you can't just, what's it called? Like, you can't just pass the parameter you can't just pass the parameter like this on the stack. It's not going to work on this type of binary. I actually changed my mind. Instead of doing it, you already saw this type of exploit from last time, so I'm actually going to do it slightly different than last time. So I'm going to do entirely return-oriented programming instead. And what we're going to do is we're going to call a syscall. So if we look up a Linux syscall table, and this is the great thing about pwning is you can do things in multiple ways. And I changed my mind halfway through doing this problem because I want to show a different technique. So if we look up a Linux syscall table, there's this syscall called execve, which basically just lets you run a binary. And we can see that, so it's syscall number 59, and we can see that that needs to be in the RAX register. And then the other parameters to the syscall are the file name, are arguments to the function, the binary, and the environment variables. Now, these two things, we don't care about them. They can just, but they do need to be null pointers. So they can't just be garbage, because if they're just garbage, like, that'll be bad news for us. And then another thing that we can do is we can pass in a file name to binsh string. And this actually is probably why the debug exists. I'm now realizing this. So, because if we use this debug, it'll let me print, it'll let you know the address of your buffer on the stack. Now can I, oh, I don't actually, I'd have to do this in Pwn Tools. Let me check. I'd like to see if what I could do is if I could send, I'm gonna get rid of this real quick. I'd like to see if I can smuggle in a string like this. We can see it doesn't trigger the debug, unfortunate. So we're just gonna have to trigger the so we're gonna trigger the debug, and then we're gonna read up until this. And we'll get our buffer leak is equal to, and what I'm going to do is I will strip off the last character, which is a new line, and then I will convert it to I will convert it to a actual integer because it's just a string. And then if I did this correctly, when I should be able to print out the leak that I got. And we can see, yep, it prints it out and it's the same address. So that means I did it correctly. And it will actually just recall main, we can see, which is definitely good for us. Now, this actually means the new buffer will actually be at a slightly different address. So I'm actually just going to lazy that as much as possible. And we're just going to gdb.attach right here. And I'm going to quickly set up my terminal for tmux. So that I can actually use gdb.attach. Oops. And so we can see that this is where the old buffer is. And now I'm going to just breakpoint inside of main, which is right here. Whoops. And continue. And then I'll just spam out of, whoops. How do I, oh no, it's been so long. How do I switch tabs in tmux?
It's Control B, N, or P, like next or previous. Tmux.
Okay, sorry about that. And I'll also have my thing after I attach in GB. I'm gonna have it, let's see, just r.send line, just some value for me to be able to find it. And then if I look on the stack, so we can see that our buffer begins. Oh, whoops, that should be plus. I'm just looking for where the buffer begins. I think it might be right here. Yeah, so we can see our buffer for X0x42 is the character for B. So all those Bs I spammed are actually right here. Did I send like 8 Bs perfectly? Oh man, I did. So we can see that this is the address. And if we take that address and we subtract where the original buffer is, we can see that it's 224 bytes away. So that'll allow us to know where our new our new buffer is going to be, which is 224 bytes. So now what we're going to do is we're going to, of course, send our pwn. So we're going to start with the null byte to defeat the obfuscator, then a bin sh string. And then we're going to send just a bunch of, I guess I'll send Bs this time. And I believe you determined that it was D8 we needed to go, but we're 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, if I counted right, extra characters. So and then after that, we're going to want to send our Rop chain, which I'm just going to start right here. And I'll explain that momentarily. But I just want to make sure that this works real quick first. So I'm just going to actually start. I'm just going to pop like a garbage. 6, 7, 8. I'm just going to pop like a garbage value in. And if I do this correctly, oh, whoops, I actually want to print out. I'm going to print out what I think. So like last time I checked, I actually needed to go 224 bytes down from where my leak was to get to my binsh string, because I'm actually starting with 1 byte. It's going to be 223 bytes, I think. So print bin sh location. Oops. And I'll just set up that to be 23. And we'll see if that actually works correctly. Whoops, I did something stupid. I forgot a comma. And let's see, so I will wait until the read, I'll breakpoint right after the read syscall, continue, and then I'm gonna telescope the stack, and I'm gonna then, let's see what's at this location. And if I did it correctly, yep, we can see that it's actually binsh string. So I'm able to correctly determine where my binsh string location is on the stack, and it's consistent, and it will always be 224 bytes, because when you call a function, like the number of bytes it differs by is the same. I'm actually going to check real quick to see if I overwrote enough to overwrite the return pointer, and it looks like I did. Oh, I'm off by 1 byte, it seems. So I actually have 1 extra byte written right here before the values that I actually wanted to write. So it looks like I need to go 1 further. So maybe I miscounted, and this is actually 9 characters. So that's, and I'm also using P32 when I should be using P64. But of course that doesn't matter anymore. So now we're going to show one of our final tricks, which is a Rop Gadget Generator. So I'm actually using Ropper 2. And if we look at Ropper 2, when I run it on the binary, we can see what it does is it just generates a like a large chain of possible, what? Oh, I'm so dumb. It just generates a large chain of possible Rop gadgets. Now, let me open up another terminal actually so that I can easily both edit my stuff. So if I'm editing my solve script, and then I check out the Rop my Rop gadgets. So what I need to do to call the syscall, like I mentioned before, was I need to get RAX into the value of exec VE, which is 59. So the first thing I want to look for is a way to set RAX, and I can see I have it right here, pop RAX ret. So pop R, and like I said before, the binary is actually no pi. There's no pi, which means that I can literally just, this address right here will be the actual address in the function. Now, if the binary had pi, this would actually be an offset, and we'd have to do a leak, but we don't need to do that. So what we're going to do first is we're going to return to this address, and then so when we return to this address, it's going to pop a value off the stack, which we want to be 59, because that's the syscall we want to call, which will execute a function, and then it'll return to another address. And then this time, what we're going to, and this, for this address, we're going to run a return to an address that lets us set the next parameter we want. So we need to set the file name. So we know the file name actually needs to be in the RDI register for syscalls on Linux. So we can find that there's actually a nice pop RDI gadget. So I'm going to return to that address. And then I'm going to add in the address of our binsh location, which we tested before was correct. And then finally, we need to have RSI and RDX be null. Now, sometimes those will actually work for you, like they'll already be null for you. In this case, I'm not going to assume anything, and I'm just going to set them to null explicitly. So we can see this gadget actually right here is a pop RDX gadget. And what it'll do is it'll pop RDX and then pop R13 and then return. So what I'm going to do is I'm just going to set both of those registers to null. Now we don't actually care about R13, but we don't appear to have like a gadget that only does pop RDX, just this one. So we actually need to have just 2 nulls on the stack for it to pop off. So one of these zeros will get popped into RDX and one of these will get popped into R13. And then we're just going to do the same thing with pop RSI. And that's also another one where we just want to pop 2. And then the last thing we want to do is make a syscall. So we luckily just have a gadget that allows us to make a syscall instruction. And then this, like I said, is forming a Rop chain. So this right here, this is a pop REX gadget. It'll pop this value off the stack, and then it'll go to the next, and then it'll return, which returns to the next address on the stack. This will pop into RDI, I believe it was. It'll pop our binsh string. It'll return to the next value on the stack. This will pop into RDX, one of the zeros, pop into R13, one of the zeros, then return to the next value on the stack. This will pop into RSI, one of the zeros, pop into R15, one of the zeros, and then return the next address on the stack. And the next address on the stack will be a syscall instruction. And this will have all of our registers set up correctly to make a syscall to exec VE with binsh as the parameter. And if we look up the exec VE syscall, just like on a man page or whatever, we can see that the exec VE syscall is used to execute a program. So this is definitely a very good syscall for us to be using. Now, and this, like I said, this right here, this list of gadgets, this is just code that's already in the binary that we can jump to. And you can use Rop Gadget finders, like I use Ropper2, but there's also a tool called Rop Gadget 2, I believe. Which will do a similar thing. So either of those tools is definitely like good for you. So we can see there's Rop Gadget 2, which is another tool. There's a few other tools, so just find one you like. I use like Ropper2. So what we can see is we're going to have this whole chain of different gadgets we're going to execute, and hopefully it'll call binsh if I did this correctly. We'll find out momentarily if I did this correctly. Now, and I will actually, let's see. So I'm going to run the solve real quick. I actually will boost the size of that. Whoops, a little bit. So we can see, so I'm going to breakpoint on here and continue. And I'm just going to wait until I get to the end of the function, actually. Oh, I should have just. Now we can see actually that Jeff is telling me the first return is pop REX. So that's definitely good for me already. Whoops. That's definitely good for me already. So I'm actually just going to, oh, this is another call instruction. So I'm actually just going to break point on this return right here at the end of the function so I can stop stepping through instructions. So now we're at the end of the main function. And like I said, so you can see what our stack looks like is we have a bunch of our gadgets and all of these values are going to be popping off. So we're going to return to our first gadget. It's going to pop into RAX, the value 59, which is 3B. Then we're going to return. That's going to go to our pop RDI gadget. Now, if that worked, we'll see it'll pop our binsh pointer into the RDI. Then we're going to go to our pop RDX gadget, which will set RDX to null and also R13. We don't really care about that. And then this gadget will allow us to set RSI to null. Boom. And then R15. We don't really care about that. And then the final return is going to hit a syscall. And then we can see, so we have REX. And so for our syscall, we have the syscall number set up. We have the first parameter to the syscall bin sh. We have the other two parameters, RSI and RDX, set to null. And hopefully, if this works, we can see, okay, it's executing a new program, bash, blah, blah, blah. So we can see that it did work. And now if I tab over here, we can see that I got a shell. So it looks like we were successful. So that is actually the final demo for today. I'm just going to do a quick conclusion. So the first demo was just a simple buffer over. Whoops. The first demo was just a simple buffer overflow, where all we did was, of course, is we just overflowed the buffer and then literally just a ret to win went straight to the shell function. The second demo, which we did today, which was slightly harder, was a one where we leaked out the location of libc. So we called putS with getS as the parameter. We were able to determine the remote libc by going on the Libsy database and looking up the address of getS. After that, what we were able to do is we were able to call the system function with the parameter bin sh by looking on the Libsy database website and determining what the offsets from getS to system and a bin sh string were. And this is also exemplifies a useful pwning trick where we actually return into the main function, or in some cases it might be the vulnerable function, which is a useful technique because it will allow you to basically loop a function. So you can get a leak and then you can return into like main or vulnerable function to redo your exploit. And then for the third binary for today, what we did was we used return-oriented programming, which is a technique where we return gadgets and we use a bunch of gadgets to chain. And this time we didn't actually use a libc function. We used a syscall to execute a binary. And what we did was we set up our syscall and then returned into it. And we actually used this built-in debug feature in the binary to leak the location of our buffer on the stack, which is useful because it means that we don't have to actually do shenanigans to find where the bin sh string is. So another technique, if we weren't able to leak a buffer on the stack, is we could actually, sometimes there might be Rop gadgets that allow us to print out our location on the stack, or sometimes there might be Rop gadgets that allow us to just move the stack into a pointer. Like say there was a gadget that did something like move RDI RSP. This would allow us to move the value of RSP, which is the stack pointer, into RDI. So if we saw a gadget like that, then we could do that. Or another technique is you can actually do a libc leak like normal, and there's bin sh strings in libc, so you can find a pointer to one of those. And that basically is it for the pwning workshop for today. Maybe if I get a chance, I'll do a third one of these. Thank you for coming out. If you didn't follow along today with the demo and you would like to try the problems yourself, they're uploaded on Slack and the Discord. If I get a chance, I might post my solution scripts if anybody wants to look at those as well. I might clean them up with some comments first so they're easier to understand. And thank you for coming out, and anybody that's still here, have a good day. I hope you learned something and go out there and become a better pwner.
Awesome. Thanks, Connor. So I recorded this meeting, so I'm going to upload it to Slack and then eventually the YouTube channel. I'm hoping to get all the videos uploaded on the YouTube channel by the end of this week. So you can check it out there, but it will be on the Slack by tonight, as well as Connor, will you able to send me the slides and I can post that in the Slack as well?
Yeah, I'll send you the slides. I mean, they weren't really that interesting, but
some people like to look at it, I guess, just to reference it.
I got you. I'll actually just post. Oh wait, I need to generate a sharing link, but I'll actually just post the link in the
cool.
What's it called?
Yeah, this was a great presentation. Thank you.
Thanks.
All right, so that concludes the meeting. I'll see you guys all next Tuesday at same time, 6:30. Have a good night, guys.
Have a good night.